Welcome back, quantitative analysis students. This is Mr. Marquetta, and I'm here to help you today with chapters 9.1 and 9.2. Our topics are limits, continuity, and limits specifically at infinity as the most advanced part of limits we'll study. Today is Monday, July the 12th. First, let's talk about a function. Just to refresh your memory and get you thinking about math again, a function is basically the idea of here's a variable if in an expression. If I tell you the value of this variable, you can put it into all the positions in the expression and figure out what the quantity is of the entire expression. Here we have a case where we're using C of P. You're probably familiar with seeing f of x and g of x. It could be any letters, and I want you to get used to that for our WebAssign and for our textbook. They like to use different letters. So C of P, here we have something called a rational function. Probably the most important thing whenever you look at a rational function, I want to kind of preface our whole lesson with this, is when you see a rational function, I want you to always look straight to the denominator. Make sure you look there first. When you look at the denominator, ask yourself a question. What would make that denominator 0? In other words, if I look just at this part here, what value of P would give me a 0 in the bottom? The answer is 100. And what that means is you can't find C of 100. And that's the most important thing about a rational function when you look at it, is that the denominator brings about this important age-old question about what happens when you divide by 0. Now, a lot of students make mistakes with what happens when you divide by 0 because 0 divided by a number is 0, but a number divided by 0 is undefined. And those two answers, 0 and undefined, they sound like the same idea, but they're not the same idea. 0 is a quantity. 0 is a number. If I said 0, there is an answer and you know what 0 means. If I say undefined, it means there's no answer. And there are questions in life that have an answer of nothing and have an answer of I don't know. And it's the same kind of idea when it comes to 0 versus undefined. I want to put you in a scenario and I want you to think with me for a minute of a basic idea. Imagine for a minute that I have candy in my hand. I have 500 pieces of candy in my hand, and I'm going to split it up amongst everybody in the class. Let's say there were 50 people. 500 divided by 50 is 10 candies each. Everybody understands division. But when you put 0 into the equation, this model still does make sense, and it can help you remember which one is 0 and which one is undefined. For example, how much candy is in my hand now? 0 candies. So if I'm going to say, okay, class, everybody gets an equal share of the candy in my hand, is there an answer to how much candy you get? Yes, you'll get 0, won't you? 0 divided by whatever is going to be 0. Now, go in the opposite direction. Let's say I have 500 candies in my hands. If I look at my classroom of empty students where there are 0 students in my class, they say, okay, students, here's 500 candies. Each of you get the same amount. How much does each student get? And the answer is, I don't know. I don't know how many students there are. I need to know how many students there are to answer that question. So it's an undefined question. I'm dividing by 0. So if you divide by 0, you're dividing up by nothing. You can't divide up by nothing. You need to know what you're dividing by. So the bottom line is, my friends, a number divided by 0 is undefined. And there is no answer when you divide by 0. In a more advanced way, that is applicable to rational functions like the one you see here, where in the denominator we have a quantity that might be 0 sometimes based on what particular value for P you choose. If, for example, you pick 100 for P, it should come out clearly to you that there's no answer, because in the bottom, if you put the 100 there, you get 0. Now on the top, if you put 100 there, it's okay. You get a very large number, 7, whatever. But that's not what the problem is. We can do a number on top as 0, and we're not worried about that number. It's not 0. We're only worried about 0 in our denominator, and that is the key to understanding limits and asymptotes and different important topics here today, is that if you believe that and follow me with that and believe that from the beginning, that when you divide by 0, you get no answer, not an answer of 0, but no answer, undefined, then the rest of this is actually going to be a lot easier, because undefined and infinity are very closely related, and they kind of mean the same thing in these contexts. Okay. All right. So let's get our feet wet, guys. Here we go. We're talking about limits. What is a limit? Okay, a limit, I want you to think about a speed limit for a minute. A speed limit would be, let's say, for example, you're driving and the speed limit is 65 miles an hour. What does that mean? Well, technically, it really only means that you can only do any number up to and including the number of 65. That's what it means. Now, when we're on the parkway and we see 65 miles an hour, we might do 70, we might do 80. Technically, you are breaking the speed limit when you do that. But that's a social norm and that's a different situation. What I'm talking about is if you see a limit is the very most it can be or the very least it can be. And when I say the very least it can be, remember it's the word the very least that it can be, not the very least that it is or the very most that it is. It's the very most that it can be. And there's a very specific difference between those two ideas. And if you can grasp that idea, it'll kind of come together what I'm about to explain for you. I'd like to focus with you first on the definition. I'm going to ask you to look closely at it. You may not have seen before the definition of a limit, so let's take a good look at it. We have a function f of x, and we have some interesting writing, particularly right here. I'd like to focus with you on this part of the writing. If you look right here, right? We have an X and then an arrow and then a C. How do I interpret that? The way you're going to say that is this is the limit as X approaches C. Now, I want you to imagine for a minute that you're in a car and you're approaching the speed limit. Maybe you're doing 20, then you're doing 30, then you're doing 40, right? You're approaching the speed limit. Approaching means getting closer to and closer to. Not necessarily getting there, but approaching is different than getting there. And that's the thing I'm talking about a lot here. So we would read this statement out loud to say the limit as x approaches c for the function f of x is the quantity L. And I want you to try to remember that limits are y values. If you can kind of connect in your head that limits are y values, limits are a lot easier to think of. What would the limit be as the variable x continued to increase towards 15? What would the y limit go closer and closer to? That is in essence what this question is asking. So I'll read the rest of it. It says, this is read the limit of f of x as x approaches c equals L. The number L exists if we can make values of f of x as close to L as we desire by choosing values of x sufficiently close to c. When the values of f of x do not approach a single finite value L as x approaches c, then we say it does not exist. That's really a lot of wording, and it's hard to grasp a limit based on that sentence. But as we continue and as I give you examples, you'll go back and read that sentence later and it'll make sense to you, okay? Let's talk about 3 important limits up front. I want you to look at these 3 cases here with me, okay? And in these 3 cases, I want to point out very important things. First, in the first place, in the first graph, you'll see right here, we have a point that is on the graph. That point happens to be 2, 3. There's 2 different ways to talk about that very point right there. You could say f of 2 is 3. In other words, f of 2 itself, if I ask you what is f of 2, you could say f of 2 is 3 because of the way this point is. In fact, you could say that about any point, basically. F of 2 means the y value when x is 2. And it is a matter of being really, really sharp with function speak like that and remembering that from pre-calc or algebra 1 or algebra 2 or quantitative 1. We talked about functions a lot. But f of 2 means what is the actual y value of the point where x is 2. Now, in this case, if you look at this one here, you'll notice that we have a hole at the point 2 comma negative 1 there. What does that mean? There's a hole there. Notice it's significantly very different than the rectangle that I see here, right? It's got a hole. Now, what does that mean? That means that, for example, if I think specifically about like right here and here, I'm going to use a stamp to try to show that. Talking about like here and then closer and here and here. See the x values as I go closer and closer with my little blue arrows. Imagine the x value is 1.8, 1.9, 1.99. There is an answer for what the y value is there. But when we actually get to 2, it drops out and there's no answer. It might be because of a zero issue like we talked about earlier. It might just be because that's how the graph looks. It doesn't matter. What matters is you see a hole there. So you may assume that there is an X value for 1.999, and you may assume that there is an X value for 2.0001, and everything to the left and right of that in that same way. But you are to assume specifically that there is no answer when X equals 2, even though if there was an answer because of the nice smoothness of that line, it looks like it kind of should be -1, but it wouldn't be -1 because it's not colored in, it's empty. These little ideas are really very easy to grasp when you're talking to a friend, but when you try to read it and understand it, it's hard to get out of a book, out of written text. So what I want you to look at is that it's a hole. And what it means is that f of 2 does not exist at all. There is no answer for what is y when x is 2. There's no answer. It's a hole there. But there is a limit. And as we approach 2 from the left, the limit is -1. In other words, if I could, and I'm going to try to sketch a little bit, so have patience with me, okay? Here I go. If I was kind of traveling along this line and I was approaching an x value of 2, see right now x is 0, x is 1/2, x is 1, and as I'm approaching and getting closer and closer, the limit as x approaches 2 for the y value would be -1. That's from the left side, If I came in from the right side, like this, try to use your imagination with me. I told you, this is crazy stuff, okay? But if I come in from the right side like this, I would say something like the limit as x approaches 2 from the right is actually -1. But again, it's not that f of 2 is -1. It's that the limit as x approaches 2 is -1. And it's the same coming from the left as it is from the right. And the way that we know that is by following the curve of the function, okay? Take a look now at our last case. And also, by the way, include with your examination that there's this going on up here. What's going on here? You'll notice I have, it looks like I have 2 points at the value x equals 2, as if I have one right here and one right here. But remember, the bottom thing is not a point. We discussed what that means. That's a hole. A hole means that if there was a point for it, if I was carrying on with the direction I was going in the path I was going of that curved line, the next thing after 1.999 looks like it should be 2, 1, but it's not. Instead, I have this dot right here, and I'm going to really emphasize this dot. This dot is very, very important because it is the answer of what is f of 2. F of 2 is 4. Actually, you see ink there for the dot. It's not colored, it's colored in. It's not a hole, it's a colored in dot. And what that means is that is the answer of f of 2. In the case on the far right, f of 2 is 4. However, the limit as x approaches 2 is not 4. As x is approaching 2, let's approach 2 from the left. Oops. I didn't mean to use a star. I meant to use the spray can. Okay, so graffiti. Here we go. We're approaching 2 from the left, all right? As I approach from the left, like right now, x is 0.8, x is 1, x is 1.1, 1.2, 1.5. And as I approach from the left, is it not the case that the limit is the y value of 1? Yes, it is. Furthermore, if I approach from the right, like this, here I come from the right, here I come. Right now, x is 4, x is 3, x is 2.5, x is 2.1. As I approach from the left, getting to x is closer to 2, y is closer to 1. So the limit here is actually 1, but f of 2 is actually 4. Okay, so it's pretty deep, huh? This is what we mean by limits and approaching. And it's kind of like, well, it's not exactly like, it's make a joke of it, It's like it's almost there and it's not, any way you can interpret it and think of it. This is how limits work. And if you have a good grasp on the idea of what f of 2 is versus what the limit as x approaches 2 is, then you'll have your right answer. Remember, both of these are y values. That limit for a, b, and c, the answer is the y number. For f of 2, the answer to f of 2 is a y number, So to recap, let's get rid of this. For the first case, it is true that f of x equals 3 because of this point. And that, not because of the point, but because as we approach it from the left and as we approach it from the right, we do get a 3. So as we approach 2, like this, or from the other side, the limit is a y value of 3. And likewise, since the dot is on the line, we can also assume that f of 2 is 3, is this actual point. All right, now for the next one, what is the limit what is the limit as x approaches 2? Okay, let's approach 2 then. If we were going to approach 2, I would start over here. I'm approaching 2, and what does the y value appear to approach? It appears to approach -1. Same thing coming from the right. If I approach 2 from the right, it becomes -1. So the limit is -1. Now, in the same context, what is the actual value of f of 2? And you'll notice for f of 2, I only have a hole here, and furthermore, I don't have a dot anywhere in the place of x equals 2 at all. So there is no answer, and it does not exist. You can write DNE for does not exist. It's the same idea as if you've ever seen Mean Girls when they say the limit does not exist. They're talking about this math topic. I don't know if that makes any sense or if that's fun to anybody. Also, for the third one, which is the weirdo, let's establish now that the limit as x approaches 2 from the left or from the right is actually 1. I'll use blue for that. So let's approach 2. Here I come for 2. And it looks like the y value was approaching 1. Like as I approach 2 this way, see how the y value is negative, then the y value is 0, then it's a little bit above 1, above 0, and then it gets to there that way. So that's what we mean is approaches. As x approaches, y changes as well. And then likewise, we could say, okay, now what is actually f of, what actually is h of 2? And you'll notice that right here, there is not a dot there, but there is a dot right here. I'll circle it big. So what is f of 2? Well, there is a dot, 2, 4. Y is 4 when x is 2, according to this function. You might see this function as a piecewise function, or with a denominator, different ways to write it algebraically. But that's the most important idea of a limit, my friends. That's the biggest concept of a limit you have to be comfortable with, is using this wording. And I hope that when it's time for you to go back and practice with limits, you'll come back and watch this video again, or maybe you could open up the PowerPoint. This PowerPoint, like all PowerPoints, is also available in eCampus for you. Go just look at it, and the answers to each of the examples are here on the left. By the way, as you can imagine, this all came right out of your textbook. You could open up your textbook and see this stuff too. I just kind of organized it so it'll be easy to explain for you guys. All right. All right, so that's what we have to say about limits. We have a lot more to say about limits, but that's just the intro stuff we need to be familiar with, okay? Now, remember when we said approaches from the left and approaches from the right? That's what we call a one-sided limit, okay? I want you to look at these cases here. Using the function's graph, determine why the limit as x approaches 2 does not exist. Now, I'm going to look at each of them one at a time, and I want you to focus with me on the limit as x approaches 2. Now, notice that in each of these, the number 2, let me try to get a good picture of all three of them, okay. The number 2, I've got it right here, meaning at this position, then 2 is at this position, and then 2 is over here in this position, right? So if we think about x approaching from the left, the image would look kind of like this. What does the y value appear to be approaching as the x value is getting closer to 2? What does the y value appear to be approaching as the x gets closer to 2 from the right? The answer is infinity. In other words, what are the y values getting closer and closer and closer to? Imagine for a minute that I was talking about right here, how this is 1.5. Look how far up we went. Imagine I was talking about 1 3/4. Look how far up we have to go to get to 1 3/4. Imagine if I could figure out what the y value is when x is 1.9999. It'll be almost infinity. It'll be huge, really big on this function. And if you look at these dotted lines that you see right here, that dotted line is something we like to call an asymptote. An asymptote, you may have heard before when you were studying graphing back in high school. An asymptote is a line that represents a guide that your function will get closer and closer to, but will never ever touch. It's this poetic thing that they'll never reach each other like Romeo and Juliet. So think of it like that. That's what an asymptote is. And here you have an asymptote, which is a guide for how from the left, it keeps on getting closer and closer and shooting up into the air. And on the right, it starts way up high and is falling down, kind of like a waterfall on the right. This is what we mean by approaching from the left and approaching from the right. The limit as x approaches 2 from the left is infinity, way up in the air. Likewise, the limit as it's approaching it from the right, coming in the other way, is also going up towards the air, towards infinity. So for f of x, the limit does not exist because the limit is infinity. There is no limit. If you figure out 1.999999 and put another 9 at the end, it gets bigger again. So you can always find another number that is not quite 2 exactly, but so close to it that you're even bigger than the last time you did it. Put another 9 digit at the end one more time, you'll get an even bigger answer for what the y value is. And that's why there is no limit. It doesn't exist. Or you could say the limit is infinity, but that's a little bit of a less than appropriate way to say infinity is not a limit. Infinity is a way to express an idea about a limit, but limits either exist or they don't. And if they exist, then they're numbers. But if they don't exist, then they just don't. You don't say they're infinity or whatever like that. Let's also talk about for g of x, if I was going to approach 2, let's approach, meaning let's go and get the spray paint can. And from the left, I'm approaching 2. And what's happening? As x is getting bigger, see right now x is maybe like 3/5, maybe right now x is like 0.9, x is at 1. Look at how y it's going down. As x is getting bigger, it's going down. When x is 1.5, it's down to -2. When x is 1.8, it's down to -3. So imagine what it's like when x is 1.999. Isn't it negative a huge number? In fact, the closer you get to 2, 1.999999, you'll get even a more negative number. So if you approach it from the left, the y value approaches in negative infinity. If you approach it from the right, meaning coming from this direction, the y value is approaching positive infinity. And in this scenario, you'll notice that approaching from the left, you get a different answer than approaching from the right. At least in the first one, they both approached positive infinity, right? But here you have one going down and one going up. That's a clear indicator that the limit does not exist. In fact, if you ever approach from one side and get a different number than when you approach from the other side, that's the best reasoning to state the limit does not exist. And that is just what happens in the third case. Take a look at the third case. I'll use red for this one. Let's approach 2 from the left. And what happens? The y value approaches 0. In fact, it gets there. And furthermore, f of 2 is 0. Good to know, right? Like we just talked about before. But the point I'm trying to make is the limit as x approaches from the left is 2. The limit as x approaches from the right is 3. I'm sorry, the limit from the left is 0. Let's put the points in, and that'll make it clear. The limit as it approaches from the left is 2, 0. So the limit is 0. Whereas here, the point that it is approaching is 2, 3. So the limit is 3. Okay? In other words, it's the y value that represents the limit. And as we approach from the left, the y value approaches 0. Look at the point, 2, 0. As it approaches from the right, the y value approaches 3. Look at the point, 2, 3. Now, it's not a point, right? It's a hole. So 2, 3 is actually not a point, but 2.00001 is a point on that line, and so on, and that's just the place where it originates. So the limit from the left is 0. The limit from the right is 3. The limit from the left is not equal to the limit from the right. And whenever that happens, just like in the second one, that's a quick, easy way to say the limit does not exist, okay? So for the limit to exist, it must be the same coming from the left and the right, and that's a theorem we're about to look at, all right? And here you have 3 great examples once again. Let's recap. I want you to think about the way this is written and read it out loud well, not out loud, but I'm going to read it out loud and read along with me in your mind these ideas. If you have a good grasp on each of these three pictures, we should be able to understand now. For the first picture, A, as x approaches 2 from the right, f of x approaches infinity, meaning y, the y value gets closer to infinity. F of x and y are the same thing. That's another big secret in math they don't tell you. F of x and y are the same thing. Okay, so as x approaches 2 from the right, y approaches infinity. As x approaches 2 from the left, meaning coming from the left, as you can see, the y values are going up and up and up. So f of x approaches infinity. Let's focus on the second one. As x approaches 2 from the right, the values of y approach infinity. I'm talking about this part right here. Whereas as x approaches from the left, as it approaches 2 from the left, 2 being the vertical dotted line, the y values are approaching negative infinity. Once again, one side, the other side, they're not equal. You know. And last but not least, here as we approach from the left, we get a y value of 0. Here as we approach from the right, we get a y value of 3. And by the way, while we're in this conversation, like we said earlier, if the limit from the left does not equal the limit from the right, then you automatically can tell the limit does not exist. Okay, so how do we figure out these limits? Well, it's really easy if you have a graph. If you're looking at a graph, it's a real piece of cake to answer questions about limits. If they give it to you in algebra, a function that's written kind of like the one with 100 minus p on the bottom, like we showed you earlier, you have to go through the work of graphing it and then look at it to answer questions like this. Or sometimes there are tricks in algebra to know how to figure out limits without looking at the graph, and we're going to do those today too. But the limits are kind of really easy to grasp in a geometrical way if you look at pictures. After you're really good with all of these ideas of example 1 and 2, the rest of the stuff is algebraic, and it's algebra that is following the model of the story of what a limit is from the left and from the right, whether it exists or not, and all those ideas we've discussed, okay? But that is our foundation, is these little definitions of how to determine when something exists and when it does not exist. That's what it's about. So let's look at limits just as if they're algebraic things, where it says for each of these starts with the limit as x approaches c. I want you to think of it as if it was the cosine, or as if it was the log, or if it was something in math that was a new idea. It just says lim, and these are the rules of lim. Now, what does it actually apply to? It means if you have a function and you graph the function and you think about graphing it a certain way, etc., and answering questions about it, etc., you could use that as the model for the definition of a limit and all that. But when it comes to just doing algebra with a pencil, these things hold, and you can use these little ideas to manipulate and make quantities simplified and so on. And that's something else you have to have as a skill set here in quantitative analysis too, is take a limit and play around with it and get answers out of it. There's a lot of practice in WebAssign about manipulating limits using these ideas. Let's talk about them each one at a time. First, let's remember that this part right here is a y value, okay? This is a y value. And that means k, of course, is the y value of the point that it would be if it could be a point. Let's also focus for a minute on what's written afterwards, and I'm going to highlight them all. The limit of what? Here is the limit of k. Here is the limit of x. Here is the limit of two things being added. Here is the limit of a product. Here you have the limit of a quotient. Here you have the limit of something with a root. The limit of whatever, the whatever is an actual function. So, for example, in part 1, k is a function. K, by the way, is a constant. Maybe it's 5. So it's as if I said, okay, f of x equals 5. F of x is 5, so that's what that would be. Or if it was the function f of x equals x, specifically, it would be part 2. If I had two functions being added, like x squared plus 1 in parentheses, and then x minus 9 in another, and I add them together, it's the same as if I just added the limits. And you can kind of move the word lim around kind of as an algebraic agent in your figuring, and that's the idea here, all right? So can we remember, guys, that a limit is a y value, okay? And that when you take the limit of something, that something is actually a function with specific directions about letting x approach a particular value, like c. And k and c are both constants. What I want you to remember from this slide, guys, is that here, we'll use hearts this time. If you take the limit of a number, the answer is the number. What is the limit as x approaches anything of 48? The answer is 48. Very simple, right? Okay. What is the limit as x approaches 17 of x? The answer is 17. In other words, if x is approaching a number and then the actual thing you're taking a limit of is just x, the answer is plug c into x or whatever it is. So here's another easy one. The limit as x approaches 55 of x would be 55. Okay, so parts 1 and 2 are pretty easy. It's like an easy way to slash out an algebraic idea of canceling happens there. This one is telling you if you had the limit of two different things being added, like say, for example, the limit of x squared plus 10. In fact, I think I should probably write some of these out. I'll write them out to make it clear for you. For this part of our lesson, I'm going to ask if you could go ahead and click on the top right where it says view and make sure that you're looking at speaker view. That way you'll see a nice clear image of what I'm writing here and it won't be small. That'll maximize this image on your TV, what you're looking at, okay? What we're trying to say is for the case of a limit as x approaches a number like 3 or something like that, and we have in here a sum. What you could do is you could basically think of it as the limit of this and then the limit of that. In other words, this is the same as, and carry on with the whole part of the limit. See how I write all of that in there? So in other words, it's a little bit like the distributive property, but it's not the distributive property. Please don't call it the distributive property. It's limit theorem number 3, which is the one where it says if you have two things being added, you can just take the limits of each of the individuals. Likewise, if it was minuses, remember because it said plus or minus. So imagine for just a minute that this was minus in there. Well, you could just put a minus here and it could work the same way. That's what we do. If you also wanted to think about limit number 4, limit rule number 4, which is this one I'm talking about now, you'll notice that if you multiply them, you can kind of write them as multiplied as well. So that would look kind of like this. Whereas if you had a thing like the limit as x approached 5, I'm making new numbers up just to make it interesting, of like the square root of x times 17x to the 4th, right? Well, you can write that as the limit as x approaches 5 of the root of x times the limit as x approaches 5 of 17x to the 4th. What is my point? My point is if it's multiplied here, you can take the limit idea and give it to each thing and multiply the answers. You can also do that with division. Little case looks kind of like this. Say it's the limit as x approaches 13 of 4x squared over 50 minus x. Well, you can call that the limit as x approaches 13 of 4x squared over the limit as x approaches 13 of 50 minus x. In other words, you're applying the limit to the top and the bottom. See the idea? And these are little tools of the trade to simplify limits that you can use. Right? Last, of course, for part 6, you'll see there we have one more case, which is saying if you have a root, you could take the root off of the function and put it over the entire function, which is the one you're looking at there. It's the same idea. It would be just what you're looking at. I'm just to give you one case of it. For example, you say the limit as x approaches 7 of the square root of x, right? That is the same as the square root of the limit as x approaches 7. See what I mean? Like, in other words, you can take the root and make it apply to the whole limit instead of just the function inside, is the point. So these are all very basic little rules, and you'll see as you start manipulating them and playing around with limits, and they ask you to simplify how they come into play. And it's actually pretty straightforward after you start playing with them a little bit. Oh, I got it. I understand how it is. Kind of like when I did logs before. If you've ever studied in pre-calc, the sine, cosine, and tangent is not that different than this. It's kind of the same idea, right? Polynomial functions and rational functions. So what you're looking at here is two different kinds of functions that we're going to focus on. Now, there are a million different kinds of functions, but for the purposes of studying limits, it's important that we kind of divide the functions all into two different kinds of functions. There are polynomial functions and there are rational functions. We're not going to focus our attention on functions that are trigonometric or logarithmic or logistic or any of the other kinds of functions that there are. We're going to only focus our attention for now on polynomial functions and rational functions. So I want you to have a solid grasp on what these two things are, because if you know what this means, you could look at a function, classify it as polynomial or rational, and then say, since I've said it's polynomial, this is what I do. Since I've said it's rational, I know what to do now. Okay. The polynomial function is the easiest one. The polynomial function is the function that you're familiar with. Think of a factoring example. Think of any kind of basic function. I'll give you some examples right now of polynomial functions. Polynomial functions are those functions that have coefficients and variables, and they have no divisions. A very basic one would be 5x squared plus 7x minus 9. If you want to go a little crazy, you could have 25x to the fourth plus 15x squared minus 9x plus 1, but they're like a list, like you see here. Also, FYI, the constant function also counts. And the identity function, of course, also counts. So in other words, it doesn't have to have x in it, and it doesn't have to have, it can be a monomial, a poly, of course. Poly means many. 1, 2, 3 is a trinomial. This is a quartic. It has, because it has a 4 as its highest power, but it also has 4 terms. But this is actually a monomial. In fact, it's a constant, and so is this. So these are all great examples of polynomial functions. If you are asked to figure out the limit as x approaches any number of any polynomial function, the answer is really very simple. All you have to do is just plug the 7 right in as if you're figuring out evaluating a function. It would be 5 times 7 squared plus 7 times 7 minus 9, 5 times 49 plus 49 minus 9, which is going to be, oh, I got myself into an ugly problem there. Let me just get that answer quick. 5 times 49, 245 plus 40 is 285. So to figure out a limit of a polynomial function, all you gotta do is take the number and put it right in as if you're finding f of x, as if you're finding f of 7. It's the same. And that's why it's written in just this particular way. The limit of f of x when x approaches c is simply f of c. In other words, just go ahead and plug it right in and you'll get your answer right there like I just showed you. Now, if you look at what's written there where it says limit and it says the limit of x, it's hard to grasp, but what they're trying to say is if you can notice that it is a polynomial function, which means if you know what they look like and you know what they look like this. These are polynomial functions, right? If it looks like that, then you can get away with plugging the number in and get the answer just by putting the number right in. So you might ask yourself, well, why did I even need to learn about a limit? Well, those are the easy ones. The weird ones are the ones when you get the problem with 0, which, by the way, there was a reason I gave you a whole speech about 0. What happens when you put your value in and you get zeros? Well, then we have to go with a different situation, and that happens only with rational functions. So now I'm going to ask you, please focus your attention on the rational function. Here we have a definition. The rational function looks like this, and both f of x and g of x are polynomials. So for the most part, it's like the first function I showed you today with 100 minus p on the bottom. It's a polynomial on top of a fraction, the fraction line, and then another polynomial on the bottom of it. The way it works with that is you basically plug the numbers in like you did before. When it was a polynomial function, you plug the number 7 in everywhere or whatever the limit is approaching everywhere and you get your answer. But if you're doing it to a rational function, once in a while, you'll get an undefined answer. And we're going to talk about how you deal with that. If you don't get an undefined answer, that's great. The answer is the thing it turns out to be. You'll see a couple of examples of that today too, where you get an answer and where you don't get an answer. But what's really important here is not the polynomial function, because that's a cinch. We can do that. It's the rational function that gives us a headache when we're studying limits. All right. So let's elaborate a little bit more now on that rational function. Remember, it looks like this. This is our rational function. And we're going to work now on two different indeterminate forms. I want you to look at that wording, indeterminate forms. An indeterminate form is a form or a structure that you can't figure out. It's indeterminate. And there's two kinds of indeterminate forms. There's 0 over 0 and a over 0. In other words, what that means is when you go and attempt to figure out what the actual value is of this limit, and you plug x in and you get a number for f of x on top, and you get another number for whatever's on the bottom. If they're both zeros, then we call it the 0, 0 indeterminate form. If the first one is a number, like 71, okay, and then the bottom is a number of 0 only, you're talking about the a over 0. In fact, this indeterminate form writing should be written again right here in type 2, and it should say a over 0 writing. But again, this came right out of your textbook. A over 0 indeterminate form is a little bit different, but both of them basically require the same idea. You always do the same thing. You try to factor and cross things out so that the problem isn't there anymore. That is the whole purpose of this whole thing. If you can use factoring, which is a skill set that you learned back in high school, the F word, remember the F word from high school math? Factoring, yeah. One of the worst cases of lessons in high school that students really stumble more than any other topic I've ever taught in high school math, then factoring is the worst one. Factoring is coming back to haunt you, my friends. Here it is. And it's the way that you simplify indeterminate limits is by using factoring. So in recap, right now I'm going to focus on this part. If you get 0 over 0 when you substitute, what you do is see if you can factor and then try to reduce. Usually the thing that you can factor is x minus c. In other words, if the denominator is 100 minus p or whatever, it's usually just the thing that you need so that it crosses out just right. Usually a limit is set, like if you take a limits test, it's set up to have things that cancel due to factoring. So look for factoring tricks, right? Also, we have the other case, which is the determinant form a over 0, and that's right here. I'm going to read this out loud and we'll talk about it together. If the top is not 0 when you plug in, that's what this is trying to say, but the bottom is, that's what this is trying to say, then the limit does not exist. And in that case, we can assume that it becomes unbounded x approaches c. So in other words, we can stop right there and say that x equals c is a vertical asymptote. So if we can tell that the top is a number and the bottom is a 0, then we can assume that it's unbounded x equals c. For example, if it was x approaches 9, it's unbounded x equals 9, meaning the vertical line at 9. That's where it goes up forever or down forever. All right. Now, let's see if we can put this into practice. Right? These examples are in your textbook, and when you do your WebAssign homework, they'll be very closely related to all of these cases. I'd like to work through each of these cases now with you one at a time. Also, all of the answers are all right there. And after we go through examples 3, 4, and 5, we're going to take a very short break, and then we'll come back and finish our lesson. All right, my friends, let's start with example 3, which is asking you to find the following limits if they exist. Our first limit looks like this. All right. Now, this is clearly a polynomial function. So what I'm going to do is I'm going to substitute this x value of -1 directly in every place I see x, as if I was finding f of -1. The result would look kind of like this. And now I would like to mention here, please note my outstanding penmanship. I'm trying to be very, very clear in my writing, and I always emphasize this with my students. Believe me when I say, when it comes to writing math, If you have very clear handwriting and you take pride in the way that you write, you'd be surprised how much easier it is to understand. And one way that you can do that is make all of your writing very clear. Another way you could do that is make sure your pencil is nice and sharp. Another way you could do that is try to use parentheses when you mean multiply. When you use the dot, sometimes it can get like lost. You know, you don't want it to get lost. You want to be very clear about what you're saying. Next, -1 cubed is -1. And -2 times -1 is 2. -1 plus 2, I learned that in kindergarten, the answer is 1. So the limit is 1. The y value is 1. And in this case, we do have the point since it's polynomial, -1 comma 1. So can we remember that when you're asked to do a limit, that you always plug it right in like it's a function and see what happens first? This is the limit as x approaches 4. And you'll notice this time it is a rational function. Wow. Well, what do? We talked about rational functions. Well, before we start panicking, let's plug 4 in and see what we get. Do we get any problems? Let's see. Everywhere I see x, I'm going to put a 4. 4 squared minus 4 times 4 all over 4 minus 2. This is going to be 16 minus 16 all over 2, which is 0 over 2. Now, I have a very big question. What is 0 divided by 2? Remember what it was like when I had no candy in my hands. If I divide it by 2 people, is there an answer? Yes, there's an answer. Everyone gets no candy. The answer is 0. Has nothing to do with limits or indeterminate forms at all. It's about arithmetic. 0 divided by 2 always will be 0. Now, if this was the other way around, 2 over 0, then I'd have an indeterminate form, and I start thinking about trying to factor and make things work and change things. But we didn't have that issue this time. And as you can tell, this is the first example. These are supposed to be the easy ones, of course. And don't be afraid when you see 0 over 2. The answer is very simple. The answer is just 0. If it's 0 over 8 or 0 over 29 or 0 over pi, it's always 0 on top. It's going to be a 0. All right. So guys, that is example number 1. Example number 3. Now let's take a look at another case. We're looking at example number 4 now. And in example number 4, the first limit looks like this. X approaches 2 of x squared minus 4 over x minus 2. Okay. Okay, well, a little red flag is going to go up. This is a rational function, so it might have an issue, So let's take a close look and start the way that we always start any limit, by plugging 2 into every position of x as if it was just evaluating f of 2. That would make it 2 squared on top and 2 minus 2 on the bottom, which would make it 4 minus 4 over 2 minus 2, which would make it 0 over 0. This is an indeterminate form. What does that mean? It's an indeterminate form. Well, it means I have to do something else. Maybe I can use the F word, factoring, and see if I can somehow simplify it. Let's see. Now, if I look at this, do I see anything in this limit that can be factored? And some of you might be looking or remembering, if you were sharp in factoring, that the top is a case of what we call difference of 2 squares. If you forgot that, let's take a little bit of a walk down memory lane here, back to the 11th grade. Difference of 2 squares, factoring, goes like this. If I have 2 things that are squared and I'm subtracting them, I can take their roots and add them and subtract them like so. That can be applied here because x squared is a perfect square and 4 is a perfect square. The root of x squared is x and the root of 4 is 2. So that makes this limit now look like this. It's now the limit as x approaches 2 of x plus 2, x minus 2. And the bottom is still x minus 2. So see how I changed this expression, x squared minus 4, into this expression using factoring, which is a pretty deep technique that you're supposed to have known by now, which everybody kind of fumbles a little bit with. So don't worry if you're a little bit lost in that. But if you forget factoring techniques, you could always go back to chapter 0.6 in your textbook. Chapter 0.6 has some great lessons about factoring. And then, of course, if you need to, we can always talk after class about factoring methods as well. All right. Now, can I do anything to simplify this? Of course I can. This cancels very nicely with this. And now I have the simple question, what is the limit as x approaches 2 of x minus 2? And to finish that, I have to plug the 2 in. I'm going to just come up here and finish. If I plug the 2 in, it becomes 2 minus 2, and the answer is 0. So my solution to this question certainly is 0. It's not 0 because of this. It's 0 because if you factor, it does cancel, and you do get this. Now, that being said, my friends, if you try to factor and it doesn't cancel, which happens very often in calculus, then you say it does not exist, or you investigate with a graph. That won't happen here. Well, it might happen here when you're doing your WebAssign. But in other words, if it doesn't simplify this way, then we're going to say it does not exist, or we're going to use a graph. All right? For the second one, we have a similar case of 0 over 0 indeterminate form. The second one is the limit as x approaches 1. And our rational function this time is x squared minus 3x plus 2 on top. And on the bottom, I'm getting x squared minus 1. Your first step should always be to evaluate the limit as if it were a function by replacing every x you see with the number we are approaching, which is 1. That would turn this into 1 squared minus 3 times 1 plus 2 all over 1 squared minus 1. Simplify, it becomes 1 minus 3 plus 2 over 0, which is 0 over 0. And again, we have our indeterminate form. Now, let's talk about factoring. Can we factor anything up here? Well, we have one method of factoring that might be called Berry, or you could call it A equals 1 trinomial. Different textbooks call it different things. But for the most part, this, we can figure this out if we can find two numbers that multiply to make the number 2 and add up to make the number -3. Those two numbers are -2 and -1. If I take -2 times -1, it gives me 2. If I take -2 plus -1, it gives me -3. If you put it into this formation, you're home free. In other words, this factored is this. The last thing you're supposed to do is check it. If you check it with the FOIL method, this is x squared, this is -1x, and this is -2x. That's -3x. And last but not least, I have -2 times -1 is my 2. So you'll see this is the result of that factored. Likewise, by the way, while we're in this conversation, let's take a look at this. And once again, let's do our difference of two squares. Again, the difference of two squares for x squared minus 1. X squared, the root is x. 1, the root is 1. So x plus 1, x minus 1. So what does that all mean? That means that the limit can be written like this. It's the limit as x approaches 1 of our numerator over our denominator. And use a little green for emphasis. Can you see the algebra happening here? Right. So now what happens? We have a new limit. The limit will be x minus 2 over x plus 2. Now again, we try to put the 1 in for the x value. It's 1 minus 2 over 1 plus 2, which is a very uncomfortable -1 over 3. And -1 over 3, if when we grow up a little bit, we're not afraid to call that -1/3. See how I took the negative off of the top and put it to the whole fraction? This is a great example of how to figure out a limit of an indeterminate form. We have a limit that we see as a rational function, so we think immediately, we might have to do some factoring. We attempt to put x in as 1, hoping we won't have to do factoring, and we do the arithmetic and we wind up with an indeterminate form, which indicates that we certainly must do factoring. So what we do is we attempt to factor the top and bottom. Sometimes they don't both factor. This time they both factor. This one factors nicely using the Berry method or the A equals 1 trinomial method, as you see here, into this expression. This one factors according to the difference of two squares method from factoring, which gives you this expression. If we replace the two polynomials with these two factored forms, the limit appears like this, and then these things cancel out, and we have alleviated the problem of divide by 0, and now you can finish and get your answer, and you get -1/3 as a solution. Also, -1/3, if you have to get an answer that is exact, make sure that you enter into WebAssign 1/3. Don't put 0.33. It'll mark you wrong. Okay. And we have our answers there. Oh, I don't know how I have. Oh, I think I have the incorrect answer here. This should be -1/3. It says -1/2. Sorry about that, guys. But you do have your answers, so you could come back and check in that way. And now let's talk about this last form, a/0, where we're going to use a table to find our limit. Now, try to remember what we talked about when we approach 0, when we approach the value from the left versus as approaching it from the right. Think about the number 1 for a minute. Let's approach 1 from the left, and let's approach 1 from the right. If you approach 1 from the left, I want you to go to the left of 1, like -10, -9, -8, and get closer and closer to 1, -3, -2, 0. You're getting closer and closer to 1, 0.1, 0.5, 0.9, 0.99, 0.999. I'm hoping that that's making sense to you, because that is the whole idea of what you see right here. See how we are approaching 1 from the left? Meaning that we're going to the left of 1 on the number line and choosing numbers over there and choosing numbers closer and closer to 1 as we march toward the number 1. If we were going to approach 1 from the right, we would go above the number 1, maybe start with 10 and come back 10, 9, 8, 7 back until we get to 5, 4, maybe 2. And now how about what's between 1 and 2? 1.5, 1.2, 1.1, 1.001, 1.0001. Now, do you see what's happening here? Is we are approaching it from the right here. And as you approach it from the right, all of these different values that you can choose as x values while you're approaching, you can take those values and actually put the answers, put them into the function and get these answers. This is very easy to do with a table, especially in Desmos, which is our online graphing calculator, which will take any function and give you a table of any values you choose. It's very resourceful, especially when the arithmetic is complicated like you see here. Notice we have an uncomfortable rational function, x squared plus 3x plus 2 divided by x minus 1. To figure out the value of that when x is 0.99 is very cumbersome. It's calculator work, and it's a lot of digits, and it's a lot of writing with a pencil. Our Desmos will do that quick and easy for us. I'm going to show you how to do that today. But before we do that, I want you to grasp the concept. Can you see that as you approach 1 from the left, the y value spins out of control towards -infinity? Look right here. Look at this figure right here. It's humongous. Likewise, if I approach from the right, look at this figure, also humongous, but positive. So think carefully about right here where it says f of x will approach -infinity, meaning y values will approach -infinity. Look at the star. As x approaches -1, look at the red box as x approaching -1. And likewise, here we make a statement that the y values approach positive infinity. Look at the star by 60,000 there as x approaches 1 from the right. And I want you to look very closely right here at this adorable little tiny exponent sign right here. It's really small. It's really easy to lose sight of. Let me get an arrow. See it in there? It says x approaches 1, and there's a little minus sign like an exponent. We read out loud from the left. Same thing here. We see x approaches 1 with a little tiny plus sign. We read that out loud as x approaches 1 from the right. And also here, x approaches 1 from the right. It's like that little plus sign is part of the arrow, and it means approaching in mathematics. So can you look closely at that and remember that little negative sign really does mean all the world. It means that you're approaching it from a specific particular direction. When it comes to doing something like this, if you plug in 1 into this function right here, you're going to get a number on the top. Specifically, the number you will get is 6, actually. And on the bottom, you're going to get 0. You're going to have the indeterminate form 6 over 0, which represents the form a over 0, meaning the top is not 0, but the bottom is 0. When that happens, your best bet is to just recognize that the limit does not exist and that it is a vertical asymptote at that very value. In this case, the value is 1 because we're approaching 1. And since that's happening here and up here that's not happening, we can make that assumption. So before we take our break, I just want to show you now in Desmos how you would do that. Now, Desmos is an online calculator. It will make graphs for you, and it also can make tables for you. And that's what we mean by the expression tabular analysis. Tabular analysis is what you just saw in your textbook, which is here's a function. I'd like to get a lot of values for the function in a table and use it to make decisions about limits. Here you have a great scenario of trying to use Desmos to get a table. We're trying to approach the number 1, which is what you see right here. This is us approaching the number 1. The x values are going 0, 0.5, 0.8, 0.9, 0.95, 0.99. If I put 0.999 in, it will be even more negative in the y. And then what happens is you start to get a sense that as I get closer to 1, the y value gets closer to negative infinity. Likewise, if I approach it from the other direction, I can put any values I want in this table. So I'm approaching 1 from the right. I'll start at 2, and then go to 1.5, 1.2, 1.1, 1.01, 1.0001. You'll see that. And as that happens, you'll see that we carry on towards positive infinity. If I put 1.000001 in there, we're going to be up there in the 6 millions like we were before with 60,000. And just for emphasis, by the way, if you did want to know the answer to what is it at 1, Desmos will tell you it is undefined at 1. So if you put 1 in, the table will yield back the answer, the word undefined, because there isn't an answer for that. Only for numbers very, very close to 1 can we get answers. All right. So I hope that makes sense. I want to show you now how to do that in Desmos, actually. Let's take a minute to do that, and then we'll take our first break. Okay. Once again, when it's time to go to Desmos, you'll go to an open browser and just type in desmos.com right there. It's easy to get to. And you can click Graphing Calculator, and now you're in calculator land here. Let's put that function in. I'm going to look at the function one more time. The function was x squared plus 3x plus 2. Now, to get the exponent, I could either come down here to the keyboard and get this function here. Then I want to show a denominator. I can do that in a couple different ways. The easiest way to do it really is to just put this in parentheses like this. Watch how I do it. And now type the slash, and there you go. Now on the bottom it was x minus 1. Now the graph is there, and that's really great to look at. Isn't it interesting? I could zoom out and get a good look at it. And you'll notice that if I put in there, by the way, x equals 1, x equals 1 is the asymptote. See the blue line? If I put in there that line, you'll see how an asymptote actually works. It's just what you think it should look like. But let's get rid of that because we don't even care about that. What we want to know is in tabular analysis what the limit would be at 1. The way I'm going to do that is I'm going to say, Desmos, I love that graph, but can you show me this as a table? The way I do that is I would go right here, edit list, and then I would press this little icon, which is the table. Now look, suddenly I have a table and I have a chance to put in any number I want. What if I want to figure out the answer? And I could delete them if I want to. What if I wanted to find out when x is 1,000? What's the answer? The answer is right there at 0. It's 1,004. What if it was 0.009895? In other words, I could put any old number I want in there. So if I'm going to try to approach 1, let's do it by putting in numbers that approach 1, like 0.5, 0.9, 0.99, 0.9999, 0.999999. See how what's happening? Y is getting more and more negative. Look at the exponents until it's basically undefined, meaning it can't understand anymore the number. That's what that means. I could do it coming from the right also. If I was trying to approach the value of 1, I'd start with maybe 2, and then do 1.5 and 1.1 and 1.01, 1.00001, and you see how it gets closer and closer. So You can use Desmos to do tabular analysis for any of the functions you can't figure out algebraically, because the idea of what a limit is still appears clear here, the way that Desmos uses geometry and coordinate geometry and the axes to be able to show you stuff. All right. So I hope you enjoyed that. I certainly did. It's one of my favorite topics, limits, because it's a lot easier than people make it. It's just a matter of really knowing your algebra skills really well, you know. All right, so for this next example, there's one little thing that's really important here, and then it does come up later on. Take a look at it and we'll take our break. USA Steel has shown that the cost C of removing P% of the particulate pollution from the smokestack emissions of one of its plants is this function. Look familiar? We talked about that function at the beginning of our class today. Investigate the cost of removing as much of the pollution as possible. And you can see the only thing really that you can get out of an investigation, just glancing at it, is that you can't remove 100% of the pollution, which is a pretty grim reality, you know. But the point is, of course, the function is set up such that if you put a number in that is close to it, like 99%, you'll get an answer, you know. But 0.9, like 99, but you can't put in 100 or anything bigger than 100, you get inappropriate answers. What if you put 500? Then you get a negative answer, and that doesn't make any sense, you know. So in other words, there are certain restrictions on models because of nature. Like, you know, in other words, you can't actually create pollution by removing negative pollution, you know. I mean, in other words, so there's a lot of ways to interpret that, but I don't want to saturate you and overwhelm you. We did make it through chapter 9.1. 9.2 is much easier than 9.1, I promise. We'll zip through it before you know it. I'm going to take a very brief break. Right now it's 5:50. Guys, if you need to go get some coffee or go to the bathroom or something like that, or take a walk outside, we're going to come back at 6 o'clock. And at 6 o'clock, when we get together, we'll start focusing on continuity and thinking about how limits work and using piecewise defined functions. All right, 10-minute break. See you at 6 o'clock. And thanks again for your close attention. Sure appreciate it. Welcome back, my friends. So let's carry on now and talk about example 7 now. We're looking at a piecewise function. You might recall learning about these in algebra. A piecewise function is basically more than one function graphed at the same time, except only parts of the two functions that you're looking at are being graphed. Specifically, the part of the x squared plus 1 curve that is only for values and points that have x less than or equal to 1 is shown. And likewise, the points of the line x plus 2 are shown only for those points that are greater than 1. What does that mean for us? Well, if we're trying to do this limits, we should do this with technology. It makes it much easier. Your best bet is to go right to Desmos and get an image immediately. This is what the graph would be of a piecewise function, as you see in example 7. Now, when you were in Algebra 2, your teachers hopefully taught you how to use a pencil and paper to sketch something like this based on that function that you're given there. And if you know how to do that, if you remember how to do that, that's great. But you don't need to know how to do that to be able to succeed at a question like this. All you need to be able to do to answer a question like this right is be able to enter it into Desmos and get a clear image of the picture, and then you can start answering the questions. Look very closely at these questions. The first question says, find the limit as x approaches 1 from the left. From the left means approaching it in this way. Here I come from the left, right? What's the y value going to be as I get to 2? As I get to 1. Now notice this is where 1 is right here, right? So as I got to 1, what was the y value here? 2. So the answer is 2 for that part. Now if I approach it from the right, let's use a different color. Approaching it from the right means coming in this direction, right? And what is the limit now? Well, what's the y value here? It's actually 3. So this time the answer is 3. That's the answer to this question here. The limit as x approaches 1 from the right. And now for the last question, what about the limit as x approaches 1? And notice there's no direction. There's no from the right or left. There's no small exponential font size plus or minus. That means from both left and right. And the answer is it does not exist. Why? It doesn't exist because the number from the left is different than what you get if you do it from the right. The limit as we approach from the left is a y value of 2. The limit as we approach from the right is a y value of 3. 2 does not equal 3, so the limit does not exist. The left-hand limit does. The right-hand limit does. The limit as a whole does not exist. Now, again, how do we do that? Well, we put it into Desmos. I'd like to show you briefly what that looks like. Let's take this function, which is piecewise, and put it into Desmos now. First, I'm going to clear all of this stuff, and I'm going to click Home to get me back to my original position. And now I'm going to enter the two pieces. The way I'm going to do it is I'm going to start by using the fancy bracket. The fancy bracket, you could find that if you look at the Enter key, it's right above the Enter key, or the fancy brackets, it looks like that. So first I have to put in the condition, which is the thing at the end. It says if x is less than or equal to 1. So I'm going to type in x, and then I'm going to get that symbol right here, less than or equal to 1, and then use a colon, and then I'm going to write in the first part. The first piece is x squared plus 1. Okay, and now I can use a comma. Notice when you come out, when you go to another page, the little highlighted brackets there, you have to go back and get in there again. Just know that. All right, every time you move away, they make assumptions kind of like that, you know. The bottom one was x plus 2, but it's for x is greater than 1. So I'll put x is greater than 1 and a colon, and I'll type in x plus 2. Oh, look, it came out of the bracket again. Close the bracket. And there's the image that we were talking about. Now, if it helps you, you could do a tabular analysis with this function, and you could get points. Or if it helps you, you could just click right on it. Or maybe you can't click on it because it's piecewise. There we go. So if you change it from tabular back to equation, you could click here and get points. And this is making it very clear. Look, as x is approaching 1, so look at the x values are 0.55. Look how x is approaching 1. Look what's happening to the y value. The y value is getting closer and closer to 2. You can really see the calculus here. It's really great that you could see that. And then, of course, we have at 1, it does give you 2. But over here, as we go towards 1 from the right, you see we're getting closer and closer to 3 after all. But the joke is on you. There is no answer at actually 1. You know, see how it never gets there? And that's because of the greater than symbol there. Anyway, that's how you go about doing that question, my friends, okay? All right. So here's something I need you to make sure that you're reading your textbook that's really very clear. Going through example 8, I want you to review this as part of your preparation, especially getting ready for next week's exam. You should be able to find limits using graphing, using a table, and also using algebra. We have two great cases here of trying to figure out limits using any of or all three of those. So for part A, if we were going to do this with graphing, I would type this entire thing in, this whole function, x squared plus 2x minus 35, etc., right into the Desmos and look at the graph. Looking at the graph, I should be able to tell that the limit at x equals 5 is 3. If I was going to do part A numerically, I would take it and use a table and get numbers like 4.9, 4.99, 4.999, and then 5.1, 5.01, 5.001, and carry on with that for part A. If I was doing it algebraically, I might factor it and see what cancels out. The same thing holds for part B. I need you to look at example 8 on your own, because now that we've had our conversation, it would just be me doing the same thing again, which you can watch the video or think about it again, but I need you to try it, okay? So between now and then, make sure you're comfortable with how graphing, about how solving limits graphically, numerically, and algebraically can be done. All the tools that you would need to do those correctly are all right here. As you can see, properties of limits, type 1 and type 2, and you should be able to make it through getting them that way. So please make sure that you read through example 8 in your textbook. All right, so that's what we have for chapter 9.1. Now we're going to talk about continuity. Continuity is a really basic topic. It's just what you think. I want you to think about the word continuity or continuous. If I say something like, we were screaming and hollering all night long, the noise was coming out of our party continuously all night long. And continuously means without a single break. You could say, oh, my kid brother was screaming and crying continuously through the night. So continuously means there's never a break. As you can see, all of these represent cases of breaks that you're looking at here. And in part A, the break happens, of course, at 2. In the second graph that you're looking at there, the limit doesn't, the function itself does not exist at 2. And there's a hole there that represents a break in continuity. And likewise, we have here a situation where the actual function is not equal to the actual limit, and that also represents discontinuity. So now a little bit about grammar and speech. Discontinuous means it breaks somewhere. Not discontinuous means that it's flowing and continuous. So you'll see wording that's easy to confuse. Just remember continuous and discontinuous. Not discontinuous means continuous, so basically continuous function is an easy, smooth roller coaster path. If you see a break in it somewhere, that's a discontinuity. It's almost always very clear looking at a graph of it. Okay, so we have 3 situations. The function is continuous if you can actually find the function. For example, is it continuous at 16? Well, if I could find f of 16 and I get an answer, then the answer is simply yes. Also, is it true that the limit is also the same? Then you have to say yes as well. So it's continuous if you get the answer of finding the function at that value, and it's also continuous if the limit exists at that value. And you kind of need to have both of those for it to be true, which is what the third thing says. Number 3 says the limit is equal to the value. So that's the scenario when you have a dot, like say, for example, this dot right here. This dot is -1, 0. F of -1 is 0. The limit as we approach -1 from the left is 0. The limit as we approach -1 from the right is 0. This function is continuous at x equals -1 because of those ideas. Likewise, this function is discontinuous at f equals 2, at x equals 2 because of the hole there. And again, this is the kind of stuff that it's just conceptual, and reading through the book and looking at diagrams will make it very clear for you. Let's look at some cases. Okay, so every polynomial function is continuous for all real numbers. Now, we already discussed what a polynomial function is. It's one that doesn't look rational. It's just a string of terms with exponents. Every polynomial function is continuous for all real numbers. So for example, y equals 5x squared minus with all exponents. It's just a line that looks like this. It might be just a parabola, or it might be a funny curve, or it might go up and down like a roller coaster, but ultimately there are no breaks in it, there are no holes in it, there are no asymptotes in it, and it's continuous everywhere. There are no points of discontinuity anywhere. So can we remember that if I'm looking at a polynomial function, it's continuous everywhere? All you have to do to find out if it's continuous is just look at it. If it's polynomial, the answer is yes, it's continuous at every value of x. Every rational function, though, however, is continuous at all values of x except for those that make the denominator 0. So if you look at example 1, you'll see situations where you're able to cross things out and such, but that's not what's important. Whether you can cross it out or not, you still have to look at that denominator and think about if it's continuous there or not. Look at this denominator. If I think of the equation denominator 4x minus 6 equals 0 and solve it, if I work through it, I'm going to get x equals 3/2. Now you know how to solve the equation. I'm not going to focus on that. But if you solve that equation, you will get x equals 3/2. What does that mean? That means when x is 3/2, the denominator is 0 and there is no answer. That's what that means. And you can find out at which particular x value there is no answer by simply setting the denominator equal to 0 and finding out what that value is that makes it 0. If you know what that value is, this time it's 3/2, then you can say the function is discontinuous at 3/2. So can we remember when you're looking at a rational function, all you got to do is take the denominator, set it equal to 0, and that will tell you the place of discontinuity. The same thing happens here. Even though you certainly can factor this up here, and you probably can knock things out, you still have points of discontinuity, particularly at -2 and 2. And the reason why is because if I took this function, the denominator function, and solved it, I would get +2 or -2. Which means that the function is discontinuous in two places, at +2 and -2. Now I'd like to focus your attention on the actual graph so that you could see what they actually look like. Here we have a line that is an asymptote right at x equals 3/2. It's hard to see that it's 3/2 looking at a piece of graph paper. You can probably eyeball it, but what if it was 17/23? How would you know what was 17/23 was the asymptote? By looking at the graph, you kind of can't see it, but you can find it. If you figure out what happens when the denominator equals 0, it'll tell you the place where it's discontinuous. The same thing happens here at x equals 2 and x equals -2. At x equals -2, we have a break and an asymptote like that. But at x equals +2, instead of a break with an asymptote, we have an actual break with a hole. Let's see if I could use this see-through color right there. Those are the two places of discontinuity for that function, for function b. And even though you're allowed to cross certain things out, it doesn't mean that it's continuous if you cross it out. Can you remember that? That's an easy mistake that calculus students make. Just because you can cross it out doesn't mean it's not discontinuous there. Uh, you have to recognize that it is certainly, after all, discontinuous at 2 and -2, even if you can cross out the 2, because you can in this case. All right? Great. All right. Now here is a piecewise function. Determine the values of x, if any, for which of the following functions are discontinuous. Now the best way to do this, guys, is to look at a graph. Don't even try to graph this on your own or do algebra to this. Open up Desmos and go right in with the syntax with the fancy brackets and the colon and the less than and greater than signs and everything that you see there, and put it in just the way you see it and take a look at it. Believe me when I say these questions are very easy as long as you use your technology to get them. Here, it's discontinuous, particularly at the number x equals 1. And you could see that's happening right here. It happens to be true that in that particular place, right here, we do have evidence that f of -1 exists. F of -1 happens to be 3, you know. But then if x is greater than -1, it's going to be all of these values. It'll always be 3, which all of these have a y value of 3 here. And then we have, of course, our open hole there to represent that that's only in the case when it's greater than -1. When it's less than or equal to -1, it's the actual dot. Anyway, we can, by looking at this picture, assume there is discontinuity specifically at x equals -1 because of the way the picture looks. You see there's a clear break. Whereas here, in the second one, you'll notice that there's a nice, and I'm going to use my spray paint can to follow it. There's a nice continuity going on here. It doesn't stop. It has an ugly corner. It has an ugly, we call that discrete. That's a discrete corner in mathematics. It has an ugly corner that's got issues with differentiability, which we'll get to, but it's continuous because for every x value, including the x value of 2, there is an answer for what the y value is. There is no break at all. It may not have a nice smooth curve. It might be a hard bump and a hard hairpin turn on the highway there, but it still is continuous there because it's flowing through. And you can't really see that. I mean, you could see that in the algebra if you look really, really close at it, but it's 10 times easier to get an image of it on a graph and look at it through Desmos, and you'll see that it is continuous. Okay, so please, guys, actively employ Desmos to get answers for questions like this one. Now we have to talk about limits at infinity. So these are some statements that happen to be true, but before we talk about that, I want to talk to you about a basic idea of what it means to let a number approach infinity. We'll talk about each of these in a minute, but first I want to direct your attention right here to this concept. I want you to think about numbers for x. Okay, maybe it'll be 1, 20, 75, 1,000, 5 million. This is the idea of letting x approach infinity. If I wanted to find the limit as x approaches infinity of 1 over x, okay, then these answers would become 1 over 1, 1 over 20, 1 over 75. What's happening to these numbers? 1 over 1,000, 1 over 5 million. 1 over each number is actually getting closer and closer to 0, isn't it? In other words, 1 over 1, 1/20th is very small, 1/75th is even smaller, 1/1000th is very small, 1/5 millionth is almost 0. So as x approaches infinity, 1 over x approaches 0, which is why this statement is such a powerful, important, strong statement. The limit as x approaches infinity of 1 over x is 0. Likewise, if I had an exponent here, it would only get to 0 quicker. So we can say p there. And if you look now at our theorems, you'll notice it starts with that very idea. First, the limit as x approaches infinity of any number is the number, but that was always true, whether it's plus or minus. But this is what's really crucial right here, guys. The limit as x approaches any number, as x approaches infinity of any number over x to the p, whether it's 1 over x or 25 million over x, is still going to be 0, because as we approach infinity, whatever that number is, c, infinity will always be bigger than c anyway. So the point we're trying to make is the limit as x approaches infinity of any formation of a number on top and x to any power on bottom, we can just assume will always be 0. And it works also for approaching negative infinity as well. So how do we figure that out? Well, take a look at these cases. If we want to try to figure these out, the first thing we notice is that x is approaching infinity for them. We're going to use this trick that I just showed you, that I know that this quantity is 0, in conjunction with all of our other rules that we've learned, to be able to get some answers now. Let's start with this one. The limit as x approaches infinity, 2x minus 1 over x plus 2. Okay, so first you might recall that if we have the limit of a quotient, we can figure out the limit of the numerator and the limit of the denominator. When you're writing these, don't forget to put that x approaches infinity in there again over and over again. It's very important. Okay? Then, if you recall, there was another formula that said if I'm taking the limit of a difference or of a sum, I can take the limit of each of the two things in there. So I can rewrite this to look like this. Okay? Now, if I try to do these, I do kind of run into a little bit of a problem, because this becomes infinity, and so does this. And I have something of an indeterminate form where I can't get my answers. So here's what I want you to do. As soon as you see that the limit has x approaching infinity in it, instead of doing it this way, I want you to start by turning all of the things you see here into fractions, and I'll show you just what I mean by dividing by the highest power of x. Right now, the highest power of x is x to the 1, right? So let's take that same situation and start by dividing through by x. This is a little bit confusing and strange, so I want you to pay close attention to it. Here's the original question. I see that it's a limit as x approaches infinity, so I think, what is the highest power of x? X to the 1 is the highest power of x. So I'm going to take the top times 1 over x and the bottom times 1 over x. This is in your textbook, and we'll see models of this in a minute in the writing. Now that you have this, use your distributive property and make this a new limit of 2x over x minus 1 over x all over x plus 2 over x. I know you're looking at me like I'm crazy, right? What did he do? Why did he do that? Let's review. I'm trying to figure out a limit at x equals infinity. The only information I know about limits at infinity is that if I do the limit of 1 over x, it's 0. So I'm going to try to use 1 over x here. And by the way, this is x to the 1 is the highest power, so I'm going to use x to the 1 as my denominator. And now I'm going to multiply 1 over x through to each thing. I get this strange writing. This is where the calculus gets a little ugly, and I need you to pay close attention. Simplifying this becomes just 2. This becomes 1. And you're looking at a very uncomfortable fraction. But now, if you put the limit everywhere, it becomes very simple. Try to use color to make this clear. We've already learned that if you don't have a variable in there, this is just 2, and this is just 1, right? That makes sense, doesn't it? And we've also established already that this must have a quantity of 0. And furthermore, this must have a quantity of 0. This has just turned into 2 minus 0 over 1 plus 0. The answer to this question is 2. Now I'm going to leave this here for a minute, and I want to talk to you about it, because this is not really very hard. It's just very strange that you're multiplying by this 1 over x. And one thing I could tell you guys is in math, we're always learning something new and weird. If you could just go with me on this and think about how I'm going to handle this limit with infinity, because infinity is not hard. All I have to do is remember the one and only one rule that I know about infinity, which is if I can get any forms to look like this, I can make them into zeros, which is what I wind up with here. So what I do is I say, what's the highest power of x? The answer is x to the 1. So 1 over x to the 1 is to be used in the top and bottom. You can multiply the top and bottom of a fraction by anything you like. That's the premise of reducing a fraction. Anyway, we do that, and we wind up with some new algebraic expressions. 2x times 1 over x is this strange looking thing. Negative 1 times 1 over x is this. X times 1 over x is x over x. And notice I didn't figure it out in my head. I wrote it there. I wrote it there because I want to think about how later on I'm going to be allowed to go like this. I'm going to be allowed to go like that, you know. So this is just 2 and this is just 1. I put them in. And I have these funny looking forms, but when I take the limit and approach it, and give it to each of the things here, like you see here, they all become simple questions. This is 2, this is 1, obviously, because there's no variable in there anyway. And this we've already defined as 0, and this is also to be defined as 0. The answer is a simple arithmetic like this. Not so simple, right? Let's do that other one, and then we'll call it a day. So what we would do for this is the same process. we'd go through and we try to get solutions by plugging everything in. The only thing I want to mention is that I see negative infinity here, so I might have a little bit of an issue, and I'm going to use graphing instead for this kind of question. Let's put it in and take a look at what happens when we look at the graph for this one. And the reason why, once again, the reason why I'm doing that is because I see negative infinity there. And I just want to use this one as a good case of what it's like to look at a graphing wise. All right, I'll put the function in. Okay, so let's zoom out a little bit. What happens as x approaches negative infinity? Well, let's take a point on this line. Right now, x is negative 3/8. I'm sorry, negative 3.8, right? Let me come back. I know you can't see me. Let me come back. Hello, here I am. So let's think about how x is negative 8.8. It's negative 16. As it carries on, negative 43. As it approaches negative infinity, is there going to be a limit for what y is? The answer is no. In fact, if I zoom out a real lot, it just goes up and up and up, doesn't it? The point is, what is the y values limit? There isn't one. It just goes forever and ever upwards that way, you know. And that's what we mean by the limit does not exist. And so for your convenience, I put here in the yellow box, those are the answers to the questions. All right. Now, doing this with technology makes it so much easier. And here, for example, 5, you have some great cases. I'm going to talk about them briefly. The pictures in your textbook, by the way, I want to mention the pictures in your textbook are pictures of a graphing calculator, the TI-86 calculator or the TI-93 calculator. Of course, we're using Desmos, and the reason why is because Desmos is a more sophisticated graphing utility. It's got a little bit sharper technology than back in the day when these were made. However, these are still excellent models and great learning materials. And if you were to graph these things and put them in a graphing calculator, they would look like what you see here. You should be able to look at these images and just briefly investigate continuity by seeing where the breaks are. I'm going to put in a couple of lines to illustrate what I'm talking about. Starting with this one here, clearly there is a line here of an asymptote. And if you use your graphing calculator or Desmos just a little bit, you'll realize that that line is at x equals -1. The same thing happens here. If you use your Desmos real well, you'll figure out that that's at x equals 1. But also there is a hole here, and it's hard to see, but you could see that when you use Desmos, and that also here at -1. And you could get that by just factoring the bottom to find out where they are if you don't use graphing utility. You could also see it here as well. X plus 1 means that right at x equals -1, we're going to have an issue with continuity. And you can see right here, there is a weird issue that looks like a bump, right? And then the last one, as you can see, it has a nice connection there. The connection does exist right here, kind of in this area. It's a bump in a corner, but it still is there. All right. So what you're looking at here, guys, is the summary of all of chapter 9.2 that you need to be familiar with. And this is everything that you need to know to be able to conquer chapters 9.1 and 9.2 WebAssign practice, which is officially now open for you to go and practice. I want to mention when you're doing your homework, please actively use the Ask Your Teacher message. I will be checking my Ask Your Teacher messages every single morning. I only check them once a day, though, in the morning. So if you start sending me questions on the day of your exam, I'm not looking at it until the morning and you're going to miss out. I need you to focus on doing these. This is not due until the day of your next exam. And I need you to work on trying to get them all done by then. And between now and then, if you have questions, you can bring them up in class at the beginning of class. We could go through them together. Or you could send me questions and Ask Your Teacher chat messages. But I am expecting that all of you at this point are ready to begin doing WebAssign number 1, chapters 9.1 and 9.2. Okay, so that's all I have for you. It really has been a pleasure studying with you guys. I am going to dismiss now, but before I dismiss, let's close the recording and let's open up the floor to questions. Once again, thanks so much for your attention, guys. It means a lot to me that you were paying close attention to my lesson when I was explaining.